Hello, y'all, and welcome to Lesson 21, Structure 1.5.3 of the DP Chemistry curriculum. Today, we're going to be talking about molar volumes and the gas law. Specifically, the molar volume of an ideal gas is a constant at specific temperature and pressure, so we'll define what that is. We will also investigate the relationship between temperature, pressure, and volume for fixed mass of an ideal gas, meaning the same amount of moles of an ideal gas, and analyze graphs relating to these variables. So we'll talk a little bit about what that means. But as we jump in, the first thing we have to do is recognize that, as we've already discussed, gases change their behavior, well, properties or whatever, with different temperatures and pressures. So for scientists to discuss gases, we created a standard. So therefore, we define STE. That means standard temperature and pressure. And we define that temperature to be 273 Kelvin. With gases, we use Kelvin, but if you want to know, that's 0 degrees Celsius. And that pressure is about 100 kilopascals, which is about pressure at sea level. Pressure at sea level. It's just under pressure at sea level, but 100 kilopascals is what we define it as. Furthermore, scientists define that 1 mole of any gas, of any ideal gas specifically, at STP will always be 22.7 decimeters cubed. Therefore, this is what we call molar volume, meaning that specifically molar volume is 22.7 decimeters cubed per 1 mole of gas. So if you have 1 mole of gas, it will take up a container of 22.7 decimeters cubed. We even have an equation that we can use for this. N equals volume over molar volume. N, of course, being our unit for moles. So the moles of a gas can be defined by the volume over the molar volume. And once again, this is at STP. You must be at STP. So how do we actually use this? Well, we can do some practice. So in example 1, we can take the volume of 0.500 mole of gas, whoops, of, yeah, it can be any gas. So we'll just say 0.500 moles of gas at STP. What is that volume? Well, all we have to do is take our equation, N equals V over MV, molar volume. And if we want to solve for volume, we can rearrange this to volume is equal to moles times molar volume. Therefore, our volume is going to be 0.500 mole times the molar volume, which is 22.7 decimeters cubed per mole, or mole inverse. In this equation, our moles will cancel out, and we will get a total volume of 11.4 decimeters cubed. So any half mole of gas at STP will take up 11.4 decimeters cubed. So this is how we can use it. We can find the volume of a gas at STP. We can do another practice. So when we say a balloon has 33.0 decimeters cubed of volume. So let's say helium, which we know acts very much like an ideal gas. So we can say how many moles? In this equation, we can just solve for N equals V over molar volume, which is just 33.0 divided by, or decimeters cubed, divided by 22.7 decimeters cubed mole inverse. Decimeters cubed will cancel out. Mole inverse will come to the top, and we get moles equal to 1.45 mole of helium. So something really quick before we move on is that you do not actually need to memorize this number. This number is given to you in the data booklet. So you don't need to remember it, but know that that is what the value is and how we use it in an equation. So that's molar volume. So what about describing relationships between volume, temperature, and pressure? The three things we actually define about a gas other than moles. Because we already know from this equation right here that moles is directly proportional to volume. As you increase moles, you increase volume. You could even say 2 times the moles would equal 2 times the volume. They are directly proportional. So if we look at a graph of mole and volume, it looks like a straight line. Oops, straight. I have a program that can do this and I forget to do it. It's a straight line. All right, so what about volume, temperature, and pressure? Well, let's start out with volume and pressure. Something you can think about before we even start is if you take a syringe. So you're going to learn about my bad drawing skills. If we take a syringe and we have a gas in here, and then we seal up the top, and you add pressure, you push that syringe down, well, the volume will decrease. It will be hard to press it down eventually. You can only push it so far, but as P increases, V decreases because gases are compressible. Gases are compressible. That might be an A, but it's okay. This is defined by what we call Boyle's law. Boyle is a scientist, and you do not need to memorize the name of the scientist, but basically, Boyle's law states that pressure times volume is equal to a constant. That is some constant. What this means that if pressure increases, well, I don't need to write it again, but basically, if one of our two variables goes up, the other variable must go down and vice versa. That way we can maintain constant. So what we say is that pressure, and this little symbol means proportional. Pressure is proportional to the inverse of volume. So if we were to graph these, pressure and 1 over the inverse of volume, we would get a straight line. But if we were to graph pressure over volume, we would get this sort of curve. And that's not a great curve, but like that. When pressure is high, volume is low. When volume is high, pressure is low. And so we kind of see this sort of graph. The last thing we can do is we can take two examples of that syringe. So if we take this syringe and we'll say this is scenario 1 and this is scenario 2. So I'll take that same syringe. So we've depressed the plunger, scenario 2. The pressure in scenario 1 times the volume in scenario 1 will be some volume K. The pressure in scenario 2 times the volume in scenario 2 will also be equal to the same K. Therefore, P1 times V1 will equal P2 times V2 because the multiplication, the product of these two values as seen by this equation, will remain constant. So how do we actively use this? Well, let's look at an example. Let's say 2.20 decimeters cubed of gas is at 100 kilopascals, standard pressure. but the pressure decreases to 80.0 kilopascals. So already we see that the pressure is decreasing. So we know that our volume must increase because these are inversely proportional. So when we plug this in, we should find that our new volume has increased. What I like to generally do is separate our scenarios. We'll call this scenario one, and this is scenario two. And we're looking for what is the new volume. So that new volume will also be part of scenario two. So I'm going to go ahead and set up my equation. P1 times V1 equals P2 times V2. I'm going to plug in my values, but before I do, I know I'm looking for specifically this volume. So what I'm going to try and do first is rearrange. I will rearrange volume 2 to be equal to P1 V1 divided by, not V2, sorry, P2. What I'm doing is dividing P2 on both sides. So this is my new equation that I'm going to use, and I'll plug in my values. Volume 2 is equal to the original pressure, 100 point. I do this point, by the way, for significant figures. We'll talk about that either in class or I'll release a video if I don't already have one. And 2.20 divided by 80.0. From this math, I can just plug it into my calculator and find that my new volume is 2.75 decimeters cubed. It has increased as we predicted. Therefore, our law holds true. All right. So with that behind us, we'll move on to a second scenario, volume and temperature. How did I do it before? I numbered it, so I'll number this as well. Volume and temperature. Before I actually get really into this one, I just want to go back to an example I used last lesson. I talked about thinking about gases like children in a room running around. As they run around, they bump into things. When we talk about volume and pressure, if you increase the volume or you decrease the volume, four kids running into, or even simpler, three kids running in a big room are going to create much less collisions with the walls than three kids running in a small room. And those collisions are what defines pressure. So when the volume decreases, the pressure must therefore increase and vice versa. I like to use that train of thought whenever I'm discussing gases because it kind of helps make it more visible. So with volume and temperature, if we think about a room and we have children running around and the other things are kept constant, so we'll say P remains constant, number of kids remains constant. If we increase the volume, so it's now a larger room, but we have the same amount of kids and we need pressure, the number of collisions to be the same, these kids must run faster. Faster movement is higher temperature. So we therefore know that volume and temperature divided by temperature should be constant. This is actually what we call Charles's law. Charles's law basically states that these values divided by one another are constant because volume is directly proportional to temperature. If we were to look at that in a graph, we would have volume and temperature, and they would be directly proportional. Therefore, using our same logic as before, volume 1 over temperature 1 will be equal to volume 2 over temperature 2. We're always going to be looking at it from two scenarios because this is how we can actually use this. Going from scenario 1 to scenario 2, we can start noticing changes. So let's go ahead and do an example. Let's take the same 2.20 decimeters cubed from our previous problem of gas at 256 Kelvin, so some ambiguous temperature. And we cool it to 100 Kelvin. What is a new volume? So what you can do is you can pause this video and try and solve it yourself. Otherwise, I'm going to get started right now. So this is volume or pressure one, or sorry, volume one, and this is temperature one. This is temperature two and new volume two. So I'm going to go ahead and try and solve these. V1 over T1 is equal to V2 over T2. And I'm trying to solve for volume, so I'm going to rearrange by multiplying temperature on both sides. Cancel out there. Volume 2 is equal to volume 1 times temperature 1 divided by temperature 2. When I plug in my values, I will get 2.20 times 100 divided by 256. When I plug this into my calculator, my new volume will show me 0.859 decimeters cubed. And this is to be expected. Generally, because the temperature decreased, the volume should also decrease. But you may even have experience with this. If you take a balloon and you blow it up and you put it in your fridge, the volume's going to decrease. And if you put it in your freezer, it's going to get even smaller. All right, moving on to our last relationship of this, relationship three, we're going to talk about temperature and pressure. So once again, I'm going to think about a bunch of children running in a room. Now, these children are moving at an average speed or whatever, and we're going to keep the volume constant. We're going to keep the number of kids constant, but we're going to increase the temperature. So we'll light a fire or something. Now, when you light a fire, people tend to run faster to try and get away from it. So they're going to increase their velocity. That's going to cause way more collisions. Now, those collisions we call pressure. And therefore, pressure will increase as temperature increases. So if we are to graph this, we'll see pressure and temperature, and we'll see that increase. This is referred to as Gay-Lussac's law, as the scientists that founded this. And much like before, when they are directly proportional, it is one over the other. Pressure equals constant, sorry, pressure over temperature equals constant. Therefore, we can say pressure is directly related to temperature. Therefore, we can also say P1 over T1 is equal to P2 over T2. Really quickly, I want to explain how these two are related. Basically, if we multiply temperature on both sides, we get pressure is equal to some constant times temperature. That constant can be anything, so we can kind of just delete it, and therefore, by deleting it, we're kind of talking about proportionality, not necessarily equivalency. So this is a little more math than chemistry, but knowing the math helps you understand how we go from one to the other. All right, so how do we actually use Gay-Lussac's law? Quite simply the same as we've used with other laws. So we start with a gas. Sorry, this is an example. And remember, you can pause it and try it yourself. At 256 Kelvin and 100 kilopascals is cooled. We'll take the same cooling to 100 Kelvin. So we'll say, what is the new pressure? Well, we'll start out with identifying scenario one. These are 1, and this is scenario 2. So we will plug them into our equation. P1 over T1 equals P2 over T2. And once again, I want pressure. So I'm going to multiply temperature on both sides so that I lose it from the right and it stays on the left. Then I'm going to do some rearranging and say pressure 2 is equal to pressure 1 times temperature 2 divided by temperature 1. So pressure 2 is equal to 100 kilopascals times 256 Kelvin divided by 100 Kelvin. I included the units this time just so you can see what actually happens with them so we understand why they leave. The units, Kelvin and Kelvin, get canceled, leaving us with kilopascal. That is why our pressure remains in the correct units. So once I plug this into my calculator, I get P2 is equal to 39.1 kilopascals. Well, that's about it. So I hope this helped you with the gas laws, learning all three of them, as well as their relationships and their graphical representations. So have a great day.